Chapter 2.3 is on Mathematical Induction. For this chapter we're doing more proofs, but this time we're showing that a recursive formula and a closed formula are equivalent. But don't worry, we're not generating formulas from sequences of numbers like in Chapter 1.2. So previously, in 2.1 and 2.2, we were trying to prove statements either true or false by turning variables like n is even or m is odd into mathematical terms like 2k and 2l plus 1 that we can actually work with, because if we just have like n plus m, there's nothing we can do with that. But if we have 2k plus 2l plus 1, then we can at least rearrange the numbers and simplify a little bit. So this time we're still doing proofs, but instead of caring about even, odd, and divisible by, we're just trying to prove that two formulas are equivalent. So this again means that we're going to be swapping out some original variable with a different equation that we can work with, and after substituting that variable out, we're going to simplify the math until we get the result, which will be more like the other statement. So we usually have two statements. One is, here's the original, and it's saying this is equivalent to this new thing, and we're trying to rearrange the numbers to go from old to new, or statement A to statement B. So let's do a review of a simple proof from last time, just so we can kind of see the steps and take note of them. So let's look at the result of summing any odd integer with any even integer is an odd integer. So the first step is to ask, how can we write this as a math equation? So let me open this up over here, and we'll just start taking some notes. So how can we write the result of summing any odd integer with any even integer is an odd integer? Well, we can say x plus y is z, so we're just kind of starting out by writing it as a math equation, and we'll say x is odd, y is even, and z is odd. So we have a little bit of math, but we still have this English down here. We want to turn this into a mathematical equation, some way that we can represent it with numbers. So here's just the simple equation. Then the second step would be, how do we explicitly turn x into an odd number, y into an even number, and z into an odd number, so that we can actually do some manipulations on them? So each of these variables will need to get its own alias. So let's represent x as 2k plus 1. So the alias for x is 2k plus 1. We'll swap that in over here once we get to that step. For even, we'll need a different variable. We can't reuse k, so we'll say 2l, and that's even, so then that will be swapped in here once we get around to it. And then z is also odd. So at the moment we can write something like 2m plus 1, but anything we do with k and l isn't going to end up as m. It might be better just to think of this as like 2 times some integer, like some int. You don't even know which int. It doesn't matter. It just has to be some integer plus 1. So here we've done that, and I just used 2m plus 1 here. But again, we're not going to get m from doing k plus l or k times l, but k plus l and k times l are both integers, so we could use m as an alias for it's an integer, but so is k plus l, or whatever. So now that we have aliases for x, y, and z, we will replace them in this original equation. So instead of x plus y equals z, we'll just swap these out. So 2k plus 1 is x, plus 2l is y, and then it is equal to z. So we'll just leave that as maybe 2, let's just do 2m plus 1, and just literally only think of m as representing the English term some integer. So when you're first swapping these out, it might not be nice to keep these in parentheses, just in case you have any minus signs that need to be distributed. But here we're just adding, so it's not that big of a deal. So let's copy this and move it down so we have some more space to work with. Okay. So the next step here, we've replaced the aliases or we've replaced the original variables with their aliases. And the fourth step would be to use algebra to kind of tweak it. So we know that we want the output to be some odd number, and these are the very most basic factors that we have. That's what we have to work with. So if we rearrange this, let's just put 1 at the end, so we at least have it kind of in the same order. We have some variables and then a +1. And then these two numbers right here have a common factor of 2, so we can factor that out. 2k plus l plus 1, and that will be 2m plus 1. So at this step, this is some odd integer, and this is some odd integer. And this is what I was saying before. K plus L isn't going to equal M because we can't combine these terms. They're not like terms. But we can say, well, M is some integer, and K plus L is also some integer, because if you add two integers together, you get another integer out. So these are equivalents. So in some ways, it might have been better not to even write this part here, in case that seems confusing to change K plus L to M. But again, 2 times some int plus 1 is equal to 2 times some int plus 1. So over here, we're going through that. We're swapping out the variables, simplifying, rearranging, factoring out the common term of 2, and now we have 2kl plus 1, and this is an odd number, that's an odd number, just some integer, which is represented here, and that's our proof. So if this helps at all, you can kind of just think about it as 2 times some integer plus 1 is equal to 2 times some integer plus 1. Okay, so these proofs are all about writing our proposition as a mathematical formula that we can do operations on. So generally, just take it a step at a time. Don't skip steps. It'll be a lot easier if you do all of the tiny steps all together instead of trying to skip over things. It'll also help you go back and look at your steps if you're stuck on something and going back through the process and trying to figure out what went wrong. So the good news is there's not really any guesswork. The only guesswork here would be just trying to convert a string of numbers into another string of numbers. We're not guessing sequences based on some numbers like we were in 1-2. We just have to be able to kind of play around with numbers and see if we can get it into a form that is, by some definition, even, odd, or whatever. So for 2.1 and 2.2, it's about getting even, odd, and divisibility. For this chapter, it is about changing a recursive statement to a closed formula. So a recursive formula to a closed formula. So let's look at this principle of mathematical induction really quick. Let P of n be a statement about the positive integers. If one can prove that, the first step we'll do is P of 1 true, and after that the next step will be for every integer where m is greater than or equal to 2. Whenever P of 1, P of 2, and P of m minus 1 have all been checked to be true, it follows that P of m is also true. So at the moment, maybe that just sounds like a bunch of garbage, but we'll actually see this in play when we're making proofs. In the end, we can conclude that P of n is true for every positive integer n. And also, let's look at this definition. A statement about the positive integers is a predicate P of n with the set of positive integers as its domain. That is, when any positive integer is substituted for n in the statement P of n, the result is a proposition that is unambiguously either true or false. So this will all make sense once we get into actually working with numbers than just looking at English. So let's go ahead and look at some examples. Okay, so this example 3a from the book says, show that the sequence defined by, so this is the recursive formula, and this is the close down here, a sub k, so a at some index k is equal to the previous item plus 4, with the starting point of a sub 1 is equal to 1, for k is greater than or equal to 2. And it is equivalently described by the closed formula a sub n equals 4n minus 3. So we have to show that these are equivalent. So we can start off by looking at the same indices. So let's look at recursive and closed. And let's say a sub 1 is equal to, well, we have 1 here, but a sub 1 over here is equal to 4 times 1 minus 3, which is equal to 4 minus 3, which is 1. Then if we look at a sub 2, it is equal to the previous value plus 4, which is 5. Here we have a sub 2 is equal to 4 times 2 minus 3. So this is 8 minus 3, which is equal to 5. A sub 3 is equal to previous term, so 5 plus 4 is equal to 9. A sub 3 is equal to 4 times 3 minus 3, which will be 12 minus 3, which is equal to 9. So if we just try to go through these numbers, it checks out that way. But how do we actually prove this with a proof? So over here, let's use m as our variable when we're actually trying to prove that one is equal to the other. We're going to kind of work with both of them. We're going to work with both of these equations, the recursive and the closed. So let's just start by saying a sub m is equal to a m minus 1 plus 4, which is just the same thing as here. And so now we need what a sub m minus 1 is. We don't have that, and we can't get it from here right now. But we do have this formula, and we can figure it out through there. So this is the recursive, and this is the closed. So we can say a sub m minus 1 is equal to 4 m minus 1 minus 3. So we're just plugging it into here. So this, if we multiply that out, we have 4m minus 4 minus 3, or 4m minus 7. So we know a sub m minus 1 is equal to this. And now we can plug it into this. So a sub, let's maybe do it down here. So a sub m is equal to a m minus 1. So we'll just swap that out. 4m minus 7, and then plus 4. And then we'll get rid of the parentheses and simplify. So this is equal to 4m minus 7 plus 4 will be minus 3. So that's our result. A sub m is equal to 4m minus 3. Now if we go and look at the original version of the closed formula, a sub n is equal to 4n minus 3. So this is how we show that they're equal to each other. We use the closed formula to get what the value is at m minus 1. We plug it into our recursive formula, and what comes out should be the closed formula. So here's 3c. Let's go over the same steps. So let's say step 1 is just to kind of check by plugging in. So plug in some values just to make sure. So if we have, let's say recursive and closed, we'll do the table horizontally this time. A sub 1, here it's 1, but if we plug it in here, oh man, we have to do all this math. So it'll be 1 times 2 times 3 over 6. So this ends up being 1 times 2 times 3 is just 6, so that also ends up being 1. So, yay, we get to work with fractions. Aren't you excited? It's always the best when we get to do a polynomial on top of a fraction. Okay, so 2. For recursive, it's the previous item, so 1. And then plus whatever that k value is, so 2 to the second, which is equal to 4, 5, here. And then over here, we'll have to say, plug in 2, so 2 times 3 times 2 times 2 is 4 times 5 over 6. So 2 times 3 right here, this is 6, and we don't have to do the rest of the multiplication. Those two cancel out. So then we get 5. So then this equals 5. So that's enough for checking those two. We don't need to really go into all of the numbers. That's just to kind of show that it works out. So next we have to think about actually getting the recursive formula and the closed formula to match. So again, let's just rewrite the recursive formula, but using m. So a at position m, a sub m, is equal to a m minus 1 plus m squared. So that's our general version. But we don't have a value for a sub m minus 1, so we're going to use the closed formula over here. So a sub n, we'll do a sub m minus 1 is equal to, and then we have to plug it in over here. So m minus 1, m minus 1 plus 1, and 2m minus 1 plus 1 over 6. And then we get to do all of the math. Yay! Okay, so this part just crosses out. So m minus 1, and this will be 2m minus 2 plus 1. So I am skipping some steps, but if you're getting lost on some parts, it might be better to not skip any steps at all. Okay, so we have these, and we can multiply them out. So a sub m minus 1, if we FOIL these, we end up getting 2m squared, so we'll just keep this other m on the outside for now. We get 2m squared minus m. Oops, I should have written these different so I don't have to erase these by hand. Then minus 2m and plus 1 over 6. Okay, great. Then these two can be combined, so a sub m minus 1, and we'll just distribute the m as well. 2m cubed. This would be negative 3, so negative 3m squared plus m over 6. So that's, unfortunately, the result for what a sub m minus 1 is. So now that we've solved that, let's say step 2 is figure out what it is. So arrows everywhere. So sorry that's not super clean, but here's step 2 over here. Then we plug in a sub m minus 1, so plug in. A sub m is equal to that whole lovely thing, so 2m cubed minus 3m squared plus m over 6. And it would be plus m squared from here, right? But if we want a common denominator, we have to multiply it by 6, so let's say plus 6m squared over 6. So then we can add these up. And then these two are the like terms, so that would be positive 3, 2m cubed plus 3m squared plus m over 6. Okay, and let's factor out this like m term. So m, we have 2m squared plus 3m plus 1 over 6. And can we factor this? Well, we probably can. Let's go ahead and say m on the outside, and we'll be able to factor this into two different polynomials. So we have a 2m squared, so that means one of these will have to have the 2 and the other won't have the 2. And this factor is just 1, so we can only really fit a 1 in here. So if we multiply this back out, we'll end up with 2m squared plus 2m plus 1m plus 1, which should equal out to that. So this is the factored version, and that will be over 6. So this is the original closed formula. We have m plus 1, and we have 2m plus 1. We could rewrite that if we want to be in the same order, but since it's multiplication, you can rearrange these in any order. So they are equivalent. So that is our proof that the recursive formula and the closed formula are equivalent. And here is another lovely problem from the book, which is number 4b. So this one is pretty much the same sort of deal. So let's go ahead and say for number 1, we're checking just the value for when the index is 1 for both of these to make sure that they're equal first. So b of 1 from the recursive side is 6, we already know that. But then b of 1 from the closed side is equal to 2 times 3 to the first and that's also 6. So that checks out for us. So number 2, we're going to figure out what this is for m. So b sub m is equal to 3bm minus 1. But we can't figure this out on our own, so we have to use the closed formula to figure out what b sub m minus 1 is. So that would be part 3. So let's sub in m. Let's verify for index is 1. Okay, so number 3 will be getting that value, get b sub m minus n from the closed formula. Okay, so from this we can say b sub m minus 1 is equal to 2 times 3 to the m minus 1. So then we have this, we'll plug it back in, that will be number 4. Plug in b sub m minus 1 back into number 2. So b sub m is equal to 3 times this part. 2 times 3 to the m minus 1. Okay, so if you don't remember working with exponents in algebra from, I don't know, elementary algebra ages ago, 3, this is basically 3 to the first, and then we can rearrange this as 2 times 3 to the first times 3 to the m minus 1. And when you have the same base and you're multiplying them, the exponents can be added. So this will be 2 times 3 to the first plus m minus 1, which these ones just cancel out here. So then this ends up being 2 times 3 to the m. So the full thing will be b sub m is equal to 2 times 3 to the m. And now we verify. So let's look at the original version. Verify with closed statement. So the closed statement is b sub n is equal to 2 times 3 to the n. And this is pretty much the same thing. So then we have our proof. Okay, and now we're going to work with summation. So these are the same kind of proofs. We're still working with m minus 1 a lot, but with summation. So there's an extra step that you have to keep in mind. So in the book it's written as this is the proposition. P of n is the proposition that if you take this sum, you'll get this as the result. So we need to prove that. But first, let's just plug in some numbers. So plug in numbers just to see how this all works. So numbers. So let's look at I is equal to 1, and I is equal to 2, and I is equal to 3. So if we have n squared, that's easy. That's the easier thing to calculate here. That would just be 1, that would be 4, and that would be 9. Now for I is 1, in this one, that'd just be the sum of the very first number by itself, so not really summing things together yet. So that will be 2 times 1 and then minus 1. So that is just going to be 1. So that's fine. Now, when it's 2, we have to remember to sum the previous number with the newest number. So if we plug this in, we get 2 times 2 minus 1. And then we have to remember that we're summing the previous value. So I'm going to put that at the end after I'm done calculating this. So 2 times 2 is 4, minus 1 is 3. And then we have to remember to also add the previous value. So this is when I is 1, this is I is 2. So that's a little bit hard to read over here. I is 1, I is 2. And then that ends up being 4. Okay, and again, we can plug in 3 into here. So 2 times 3 minus 1 is going to be 6 minus 1 is equal to 5. So this is I equals 3. And so we also need to remember to sum it with the previous two numbers. So I equals 2 is going to be the 3, so plus 3. And I equals 1 is going to be our 1. So 5 plus 3 is 8, plus 1 is 9. So these both check out. So the next step would be to take this predicate and replace it with p of m minus 1. So we're essentially going to say that if we sum all the numbers from 1 to m minus 1, and then this is going to be the same thing here because we're not subbing in m yet. So if we take the sum not to n but to m minus 1, then we should be getting m minus 1 squared back. So that comes from this right here. So we have to actually prove this. Now, if we take this back and plug it into the sum for all numbers, and if we just use from 1 to m, so I equals 1 until m of 2i minus 1, so this is again this statement, this should be equal to the sum of all of the numbers before it plus the latest version. So just like we have 5 plus 3 plus 1, we have to remember to take, I equals 2 and I equals 1 and sum those onto it. We need to make sure we're summing all of the previous numbers leading up to it. So we can just write I is equal to 1 to m minus 1 of the same 2i minus 1. But we also need to make sure we add the very last value for when I is equal to m. So then that will be 2m minus 1. Okay, so we've kind of extrapolated this out into being not from 1 to m, but from 1 to m minus 1, and then plus 1 additional element. Okay, so to solve this, we need to look at this part right here. We have a value for this. We've already put that it should be equal to the n squared up here, but with m minus 1, it'll be m minus 1 squared. So we're going to sub this in right here. So let me erase all these lines. So if we write this as an equivalent thing, this will be m minus 1 squared plus 2 times m minus 1. And then we can multiply this out. So m minus 1 times m minus 1 plus 2m minus 1. And if we do the FOIL, so m times m is m squared, m and negative 1 is minus m, negative 1 and m is also negative m, and then 1 and 1 will be positive 1 here, plus 2m minus 1. And again, keep simplifying it. M squared minus 2m plus 1 plus 2m minus 1. So this and this cancel out, this and this cancel out, and we're only left with the sum of I equals 1 to m of 2i minus 1 is equal to m squared. So this is our answer, this is our proof. Let's go ahead and copy it back from up here just so we see that it's the same. So this is the original proposition. And then we say P of m is equal to this. So we show that they are the same.